The other day, I was moving around some scrap metal. One piece was aluminum and the other was lead. And even though the lead was a fraction of the size of the chunk of aluminum, it weighed much more. And that got me thinking about the relative strength of each of them, with the aluminum being much stronger than the lead, despite being lighter. And then I had a realization that I don't really know why the metals have different properties. I'm sure it has something to do with atoms or something, but I couldn't tell you what the reason is. So in this video, I want to explore why metals have the properties that they have, and I want to test them in a weirder way. Like, you can look up the properties of them if you want, but that's no fun. So I think I'm going to try and split a lead bullet with a lead knife. So the idea is to make a knife out of plastic, lead, aluminum, and steel, and see how they hold up to me trying to split a bullet with them. And since I couldn't find a lead knife in stores, I'll have to make them. My first plan, which you can tell things have been going great if I have to start numbering my plans, was to use lost PLA casting, which is similar to lost foam or lost wax casting, where you make a part out of sacrificial material, in my case 2 halves of PLA plastic that I glued together, and then you cover it in something that can withstand the heat of molten metal, which I used plaster and sand, and then you melt the part out, leaving a cavity in the shape of that part. Now with wax or foam, just throwing it in the oven might be enough, but in the case of plastic, I think burning it out in the same fire I plan to melt the metal will probably help it be a little more successful. When the plastic's done melting and burning out, I bury it definitely not deep enough in a bucket of sand, and then start melting my lead. Now lead can be found in a lot of different places, like tire balancing weights or fishing weights, or I'm guessing lots of other weights, but not in things like gasoline or paint or most pipes before the 1980s around the entire world, because that'd be dumb. And it was about this time that I heard 2 red-shouldered hawks fighting over a piece of food and ran to go film it, because I'm distractible, and I mean they're neat, so I'm leaving it in. By the time I regained my focus, all I had to do was scrape the scum and the oxides off of the top of the lead and then cast it. As liquid metal freezes, it doesn't just turn into one uniform piece of solid metal, instead it starts freezing from multiple different locations which grow into one another and form a grain structure. Even these grains aren't technically solid metal because they are packed with atoms in a crystal lattice that has gaps in it. When we cut that crystal lattice into its smallest repeating structure, we get what's called a unit cell. The arrangement of atoms inside of that unit cell is what determines the atomic packing factor, or really just how much of that cell is full of atoms versus just being empty, and we can calculate that just with a little bit of geometry. While things like grain structure and crystal lattices and atomic packing factors can contribute to the properties of metals, the driving factor is one layer deeper in how atoms bond to one another. How atoms interact with one another is determined by the nucleus, which is very, very, very small compared to the atomic radius, or kind of the sphere of influence of an atom. It's so small, in fact, that if the nucleus of a hydrogen atom was about the size of a marble, and you took that marble and you put it in the middle of the pentagon, you'd get arrested. After they drag you about a quarter mile closer to jail and a full 150 meters outside of the outermost wall of the Pentagon, you would just be crossing the atomic radius of our marble-sized hydrogen nucleus, meaning that the only things inside of that entire area would be a marble-sized hydrogen nucleus and an electron with about the weight of a medium-sized ant. Despite being absolutely tiny, the nucleus of an atom determines how it bonds with other atoms. For example, this aluminum atom has 13 protons and therefore 13 electrons. 3 of these electrons are on the valence shell, or the outside shell of the atom, and whenever it makes a metallic bond, these outside electrons sort of pop off and disassociate, creating a negatively charged sea of electrons that the now sort of positively charged cores of the atoms are attracted to. Understanding this, we can see 3 main things that can affect the strength of metallic bonds, and to do that, we'll compare aluminum to lead. First up is the number of valence electrons that a metal can give up to that sea of electrons. Giving up those electrons leads to a corresponding positive charge in the core of the atom that is left, and then the size of those cores can impact the strength of the bonds, with smaller cores having stronger bonds. And then you have transition metals like iron, which only has 2 electrons in its outermost shell, so you would assume that it would be weak. But like all transition metals, it has an incomplete d orbital, which it can use for metallic bonds. Now, I'd go into more, but I don't know anymore, and I've already bored the metal stiff, so anyway, throwing the casting into a bucket of water made the plaster pretty much just disintegrate and left me with a knife that was more or less what I was going for. But that was kind of where the success with this plaster and sand method just ended, because every other attempt that I had either broke apart in the burnout phase, or cooled the metal too quickly, leaving voids or other errors in the casting. Now, I probably could have figured out all the kinks in this, but it was costing me a lot of plaster and time waiting for each of these molds to cure. Not only that, but I found that if I made the models too sharp, they would create stress concentrators that just broke the molds every time. That's an issue because I want to use .22 caliber bullets because they have a lot less energy than other calibers, giving the knives a better chance to survive. They're also really small, they're 0.22 inches in diameter, and if my blade isn't really sharp, they're not going to be able to split on it very easily, and I don't really want to have to sharpen lead. It just doesn't sound like a good idea. So, time for plan 2, which was sand casting. It's basically just really fine sand, which I used aquarium sand, and then bentonite clay, which is in a lot of kitty litters, ground up very fine. Whenever it's mixed together and wet down, it's basically the perfect sandcastle sand, and you can use it to tamp it over 1/2 of your part at a time to make 2 halves of a mold that can hold up to the temperatures of molten metal. This method was much less time consuming, used reusable materials, and will hopefully let me get a very sharp edge right out of the mold. It just needs a hole for the metal to get into the part and a hole for venting, and then I can realign the halves and melt down some metal and get this part made. Well, in the time it took me to order a backup battery, the metal is now solid, and the knife quality overall is really good, and the edge is sharp enough that I won't need to file this at all. So I'm going to go ahead and make an aluminum knife. It'll be a little more difficult because the temperatures have to be higher, but other than that, it should be pretty easy. Especially because we use it for all sorts of things. It's the most abundant metal in the Earth's crust, and we use it for things like soda cans and hard drive components, things that need to be strong and light, and they're also relatively cheap. And while melting the aluminum, I found out that the hawks weren't actually fighting over the food, or, I mean, maybe they were, like maybe he ordered the squirrel and she said she wasn't hungry, but then she ate some anyway. But they're a couple, and they totally destroyed a cardinal nest by my house too, so I think I'm gonna call them Bonnie and Clyde. But Bonnie and Clyde aside, the aluminum is ready to pour. I'm kidding, I'm not that dumb. After some time to cool, I can pull the mostly done knife out of the mold. But now I want a steel knife, which I definitely can't cast, and I'm not Alex Steel, so I can't just forge the whole thing, so I'm just going to roughly, and I do mean roughly, hammer this into shape and then file the rest away. Now I just need to clean up each of the knives and then drill holes where they'll mount to the handles, which I'm going to 3D print out of wood PLA filament. While making the knives, I also made ingots out of lead, aluminum, and plastic, so I can test on those first and get an idea of how the knives will hold up. Now I have a couple different options for bullets to try to split. I have a .22 which carries about 150 foot-pounds of force. I have a 9mm that goes about the same speed but is 3 times heavier, so carries 3 times the force. And then I have a 30-30, which is a little heavier than the 9mm, but is going over twice as fast, giving it 5 times the energy of the 9mm and over 10 times the energy of the .22. So ideally, I'll be able to use the 22, giving each knife a better chance of survival, but it's so thin that I might have to move up to the 9mm. And if I still can't manage it, then I'll turn the tables and try and split a knife with a 30-30 bullet. So now I have 4 knives. I have a plastic knife, which won't balance on the box and I hate it, which is basically just the blank that I used to design the 2 metals that I cast. Then I have the aluminum knife, which feels like a plastic knife that was just spray painted silver. And then you have a steel knife, which, if you've ever held anything made of steel, this one weighs what you'd expect it to weigh. And then you have the lead knife, which is weird because it weighs more than what you would expect it to weigh. So now it's just time to test these finally. Alright, testing in 3, 2, 1. Yeah, no, obviously not. I'm going to be driving out into the very center of beautiful, scenic nowhere, where I have a backstop and miles of empty space so I can test this safely. Plus, I'll be wearing all the appropriate attire and safety equipment. First up, I'm going to speed run the 22 through the plastic, aluminum, and lead ingots to see how they fare. These are set at an angle so that any blowback doesn't come right towards me. The 22 went straight through both plastics, left a small dent on the aluminum, and a little crater on the lead, so it's not looking great for a lead knife being able to split a lead bullet. On to the 9mm. The 9mm made a huge crater in the lead, almost going through, so it's not looking good for the knife. But did you see that hit? I mean, I'm a pretty good shot with this. And even with more energy, that 9mm is not doing too much more damage to the aluminum. And now finally, the 30-30. I don't know if you need me to tell you this, that's a hole. It's about the size of a quarter. And that's not a hole. I'm kind of surprised. It looks like it almost cracked the entire thing in half, though, which might not be good, because if that knife is that brittle, it's just going to snap. Alright, so now it's time to try and actually split a bullet. I'm going to start with the 22 because we saw that that did the least amount of damage, and then move up to a 9mm if I can't manage to hit the edge. I'll also be starting with what I expect to be the strongest knives, moving weaker and weaker. So at least I grazed it. It left a bright spot on the blade and left bullet fragments all up and down the target.
That was so easy.
I'm surprised that only took 3 shots. You can see a bright spot on both sides of the knife, but you can tell on the paper that the bullet isn't exactly in half, but I don't care, that's good enough. Now we're on to the aluminum. Yeah, I have no idea what happened. The tip of the knife is totally gone, and there's this weird silvery residue, so I'm going with cartoonish disintegration. I'm starting to think you can split a bullet with just about anything, because, I mean, it's a little more fragmented, but I think that still counts. Alright, finally time for a lead bullet versus a lead knife. Now, that was just a glancing hit, and it already took out that big of a chunk out of the knife, so I'd be worried about a direct hit. Now, that one looked pretty dead on and took a lot larger chunk out of the knife. I'm going to move the box up, so if it splits, we have a better chance of seeing. And there it is. It might not be pretty, it might not be in 2 even-sized halves, but I call that a lead bullet split on a lead knife, even if it's a little mangled. And we can't forget the plastic knife. Oh no, what a surprise, was my first thought, but then I noticed there wasn't a bullet hole from the bullet just passing straight through it, only the miss from earlier. So that means the bullet was at least deflected, and when the bullets go through this paper, they leave a dark mark. And by checking for that mark, I was able to find, first of all, the miss from the first shot, and then a deflection that was for sure where part of the bullet passed through, and then maybe a deflection to the right where I could have split the bullet, but I don't trust my eyes, I want to see it too bad, so let me know if you think you see it too. Knowing what we know about these metals, our results make sense. The lead is the softest, losing large chunks every time a bullet strikes it. The aluminum is more rigid, but is also more brittle, so it lost a smaller portion with one shot, but also just snapped in half with another one. And the steel, being far stronger than either of them, has little to no damage. And to wrap up a fun day of shooting, I'm going to shoot the 30-30 at the steel knife. It is worth mentioning that this is mild steel. I'm not sure if hardened steel would fare any better. Again, I think I'm going to call that a split bullet, because even though it destroyed the knife, fragments of the bullet landed on both sides of the target behind the blade. I really enjoyed making this video, and if you enjoyed watching it, then this is just your obligatory reminder to do all the things that 1,000 other YouTubers have asked you to do a million times. Have a good one.